Okay, we're going to carry on with field effect transistors, chapter 8, specifically section 8.3, JFET biasing. Alright, let's have a look what I've marked in my textbook again. On page 381, JFET biasing. You can mark again the sections that I have marked. I can, or I will, ask you at some points, as apart from marking, that you should also underline important sections. Alright, using some of the JFET parameters discussed previously, you will now see how to DC bias JFETs. Just as with the BJT, the purpose of biasing is to select the proper DC gate to source voltage to establish a desired value of drain current and thus a proper Q point. Remember, that was also important with the BJTs. We're going to discuss three types of biasing called self-bias, voltage divider bias, and current source bias. Alright, the first one up is self-biasing. Referring to figure 816, cell biasing for the two channels, the N channel and the P channel. What I want you to note is that the gates for both these devices are connected to ground via a large resistor RG, but I will point it out to you later again. So VG is equal to 0. Condition, gate source should be reverse biased, isn't it? For the N channel and the P channel. So how is this accomplished? Let's see what I've marked here in the book. I want you to mark this as well. Self-bias is the most common type of JFET bias. Recall that the JFET must be operated such that the gate to source junction is always reverse biased. This condition requires a negative VGS for an N channel JFET and a positive VGS for a P channel JFET. This can be achieved by using the cell biased arrangement shown in figure 816. The gate resistor R does not affect the bias because it has essentially no voltage drop across it, and therefore the gate remains at 0 volts. RG is only necessary to force the gate to be at 0 and to isolate an AC signal from ground in amplifier applications, as we will later see in a later chapter. Alright, let's see how it works. When the circuit is connected like that, cell biasing, I can see a current flows through RS, which is IS. IS flows through RS. If current flows through the resistor, what's going to happen? Voltage drop is going to be generated over that resistor with the polarities as shown because of the current direction. Remember now, VG was equal to 0 volts, and if the gate is 0 and the source is more positive, then I have my reverse bias condition, isn't it? Alright. So as we will see then for the self-biasing JFET, I have to determine for my biasing and my Q point, I have to determine the value of RS. And the same applies, of course, to the P channel. Current is flowing in the opposite direction. Remember, the polarities will always be also be different. So still, VG is still at 0, but now I have a negative at the source. Alright, so it is met again. My reverse bias condition is met again. Anyway, let's see what I've marked here in the textbook. On the next page, page 282. For the N-channel JFET in figure 816A, as we've seen, IS produces a voltage drop across RS and makes the source positive with respect to ground. Since IS is equal to ID and VG is equal to 0 because it's connected to ground, VS is equal to IDRS. So I can go and determine VGS, my biasing voltage, VG minus VS. VG is 0, connected at ground, and Vs is IDRS. But remember, it's VG minus VS, so I have VGS is equal to minus IDRS. So I get my negative biasing voltage for my N-channel device. Alright. For the P-channel, the current through RS produces a negative voltage at the source, making the gate positive with respect to the source. So then for the P-channel, VGS is equal to plus IDRS, which also meets my biasing requirements. Let's have a look at the example there at the bottom of the page, example 8.6. Find VDS and VGS in figure 8.17 for the particular JFET in this circuit. The parameter values such as GM, VGS off and IDSS are such that a drain current ID of approximately 5 milliamp is produced. You can underline that as well. It also applies to the JFETs. Another JFET, even of the same type, may not produce the same results when connected in this circuit due to variations in parameter values. Anyway, the solution then, VS is equal to IDRS, 5 milliamps times 220, 1,1 volts. VD, of course, same as we've used with the BJT, Ohm's laws and Kirchhoff's laws. VDD minus IDRD, and it works out to be 10 volts. Therefore, VDS is equal to VD minus VS, 8,9 volts, and since VG is equal to 0, VGS is going to be equal to minus 1,1 volt. So that's for the self-biased circuit as in figure 8.17 in your textbooks. Alright, important also on the next page, setting the Q point. Setting the Q point for a self-biased JFET. The basic approach to establish a JFET bias point is to determine ID for a desired value of VGS or vice versa. Then calculate the required value of RS using the following relationship. RS is equal to VGS divided by ID, absolute value because of the negative sign for the N-channel. For a desired value of VGS, ID can be determined in either of two ways. From the transfer characteristic curve, which we've discussed in the previous section, or from the equation 8.1 by using IDSS and VGS off from the JFET datasheet. Remember, I must give you those two values, or I must give you the datasheet so that you can find the values yourselves. Né? So those are the two methods. Let's see how it works. In example 8.7, it asks there, determine the value of RS an N-channel JFET that has the transfer characteristic curve shown in figure 8.18 for a VGS of minus 5 volts. Now in this case, the transfer characteristic curve was given. If I didn't give you the transfer characteristic curve, but I still ask you to determine the value of RS using the transfer characteristic curve, what do? You draw it yourselves, né? But then I must give you the value of IDSS and I must give you the value of VGS off, or I must give you the data sheet for that specific device so you can read it from the data sheets yourself. Then of course I just use that formula of equation 8.1 where it says ID, then I can calculate, remember? I must give you these values, or you read them, IDSS, VGS off, and please, ladies and gentlemen, remember the labeling. If you don't tell me where's IDSS, VGS off, you already lose 2 marks. Don't lose marks unnecessarily. Give me more information than I need, so that I can give you marks, alright? Whether it being a test or on the exam. Name the axis as well, ID in milliamps, VGS in volts. Alright, then at least you can plot those 2 points if you have to draw it yourselves. You know that by now, né? And then to determine further points so that you can plot it, you of course will use that formula that says At various voltage points now, you will go and determine at -1. What is ID going to be? ID is equal to IDSS in brackets 1 minus VGS, which will be then -1, divided by VGS off, which is -10 in this case, all squared. And then, of course, you will get the value and you can plot it. And if you've calculated all the values, you can plot the curve. Once you've got the curve and you've got a problem like this, you have to determine the value of RS at the VGS of -5. Please write this on the graph. There's your -5. Draw the broken line until it cuts the curve. Tell me, that's the Q point. Draw the broken line again. Tell me, that's the value of ID at VGS of -5. Okay? If you don't read or write exactly 6,25, the graph is very small. If you wrote 6.1 or 6.3, doesn't matter. Okay, I just want to see that you followed the correct method, as long as the value is close to it. But you have to make sure about the scale that's being used. Now, it's not always like this. I can see here -10, so each block there is 1 volt. But it's not always true, so make sure that you know which scale is used on the graph that's been given. Of course, if you draw it yourself, you decide yourself on the scale. Alright, so once I've got the value of ID, then I just go and use Ohm's law as in the solution in the book, and then I can go and calculate the value of RS, which is VGS over ID, absolute value. So of course it's not going to be -5. 5 divided by 6,25 gives me 800 ohms. But if you divide it by 6.1, it's going to be in the vicinity. Alright. That's setting the Q point for a self-biased JFET, and that was the first method using the transfer characteristic curve. The other method, which is easier, but I don't always ask the easier, is an example 8.8, where it says determine the value of RS required to self-bias a P-channel JFET with the datasheet values of IDSS 25 milliamps and VGS off at 15 volts. VGS is to be 5 volts. Please, ladies and gentlemen, make sure that you know that you're working with a P channel or an N channel, so that you draw the correct curve if you have to draw the characteristic curve. Anyway, then I just use the equation to determine the value of ID. So now I calculate the value of ID. I don't go to the transfer characteristic curve to read the value from the curve. So I calculate ID using equation 8.1, and then I can determine the value of RS. In this case, 5 volts divided by 11.1 that I've calculated, 450 ohms. Alright, those are the two methods. Determine the value of RS for the self-biasing JFET. Also important, midpoint bias. Remember, for the BJT, we also biased the BJT so that the Q point is more or less in the middle of the load line, for obvious reasons. I hope you can still remember. It is usually desirable to bias a JFET near the midpoint of its transfer characteristic curve, where ID is equal to IDSS divided by 2. Under signal conditions, midpoint bias allows maximum amount of drain current swing between IDSS and 0. And you see the similarity between the JFET and the BJT. So, using equation 8.1, it is shown in Appendix B, which we are not going to discuss, that ID is approximately 1/2 of IDSS when VGS is equal to VGS off divided by 3.4. So we're not going to look at that derivation. You just have to know that formula. So by selecting VGS is equal to VGS off divided by 3.4, you should get a midpoint bias in terms of ID. To set the drain voltage at midpoint, VD is equal to VDD divided by 2. Select the value of RD to produce the desired voltage drop. Here is that what they mention about RG that I said, must underline. Choose RG arbitrarily large to prevent loading on the driving stage in a cascaded amplifier arrangement as well. But even here. Anyway, let's have a look at example 8.9. Looking at the data sheet in figure 8.14, select resistor values for RD and RS in figure 8.19 to set up an approximate midpoint bias. So as soon as I say approximate midpoint bias, you already know a few things, né? About IDS, ID is equal to IDSS divided by 2, and you already know VGS is going to be VGS off divided by 3.4. You know that already as soon as I talk about setting up a approximate midpoint bias. Also, read the question very carefully. It says here, use minimum datasheet values when given. If you can recall from the JFET datasheet, they normally give you minimum, maximum and typical values, 3 values. Né? So read the question carefully. It says here, use minimum datasheet values when given. Otherwise, VD should be approximately 6 volts, 1/2 of VDD. Also important information that's given. Alright, I have to calculate the values of RD and RS. Start by midpoint bias. ID is equal to IDSS divided by 2. 0.5 milliamps, or rather 500 microamps. Remember to express your answers in engineering notations as you have learned in the first test. VGS is going to be VGS off divided by 3.4. Then I can go and calculate the value of RS. VGS over ID, 294 ohms. Then I use the formula of VD is equal to VDD minus ID RD to calculate RD. Take RD from the formula, then it becomes VDD minus VD over ID. Note that the question said VD should be 6 volts. So it's 12 volts minus 6 volts divided by 0.5 gives me 12 kilo ohms. So there I've calculated then the 2 resistors for midpoint bias. Next section, also very important, the graphical analysis of a self-biased JFET. Now remember, I can also combine this question for the test or the exam. I might give you the transfer characteristic curve, but I could also ask you to draw it yourselves given the values. Né? Anyway, graphical analysis. You can use the transfer characteristic curve of a JFET and certain parameters to determine the Q point. Q point parameters in the JFET's case, ID and VGS of a self-biased circuit. Remember, we're still busy with a self-biased circuit. So, but here it's mentioned again that last sentence that I've marked there. If a curve is not available from the datasheet, you can plot it from equation 8.1 using datasheet values for IDSS and VGS off. So please be sure that you know how to do that as well. Alright, so we start off with this graphical analysis. We'll get the circuit. I might give you the transfer characteristic curve, or you might have to draw it. Okay, so once we've got this, then we're going to do the graphical analysis. I just want to point out at this stage, this is, what type of JFET is this? N-channel, nah. You can see it's an N-channel. I can see that VGS off is a negative value. So my curve is on the left-hand side from ID to the negative side of VGS. There is not this example in your book. I've drawn it myself because I'm very good with Photoshop. So that's how I can change all the figures that you're doing for the tests and the exams. Né? So here you can see this is a P channel, so the curve of course will be on the other side. Alright? That's why I said be sure that you know, are you working with an N channel or are you working with a P channel? Because if you're going to use the characteristic curve of an N channel and try and draw the graphical analysis with a load line or whatever for a P channel, believe me, plenty of students does that. Don't be one of them. Okay, on page 386, That is important. How is this done? Now I've got this, I have to go and draw my load line. It says there on page 286, to determine the Q point of the circuit in figure 820, as I have displayed there on the board, a self-biased DC load line is established on the graph in part B as follows. First, underline, you have to calculate when ID is equal to 0. When ID is equal to 0, I have to go and calculate VGS. What does my formula say? Have we seen on the previous pages? VGS is equal to minus IDRS. If ID is equal to 0, VGS is also going to be equal to 0. Do you agree? So the first point I can plot there at 0. That's at the origin of that curve. Establish a point at the origin of graph. ID is equal to 0. VGS is equal to 0. Next, I go and calculate VGS when ID is equal to IDSS. Remember the first one was where ID was equal to 0. Next one is where ID is equal to IDSS. But then I have to go and calculate the value of VGS again. In this case, it's not going to be 0. VGS is going to be IDRS. If we look at that circuit and the value has been given, IDSS is 10 milliamps, RS is 470 ohms. It gets to a value of minus 4,7. Minus 4,7. If we can go to this one, there's the solution. There was my first point. Then I plot my second point and I draw the load line between the 2 points. And where it cuts the curve, I write there, that's my Q point. That's my Q point. And you have to draw for me how you've done this, exactly as in this example. With the broken lines, you show me where ID is equal to IDSS, I calculated the value of minus 4.7, and with a broken line, you have to do it anyway to do it accurately. I plotted my second point. Then I drew the load line, and where it cuts my curve, that's my Q point. The last thing that you show me with the broken lines is what are the parameters for the Q point. In this case, ID is 5,07. If you said 5, it would be fine. If you said 5.1, it would be fine. I know the curve is small. You won't be able to make an accurate reading. But just make sure that you're not out by a lot. Make sure of your scale. And write these values in. I don't look at your calculations. I look at this. I want to see that you're able to do it. And you have to show me how you've done it with the broken lines and putting in all the values. And don't forget to name everything. All the axes, the values, IDSS. Show me where's VGS off with a value. Tell me that is VGS and it's measured in volts and so forth. Then I can give you all your marks. If you don't give me all this information, I can't give you your marks. Okay. Alright, so that's for the self-biased, the graphical analysis for a self-biased JFET. And what we've done there basically was, now let's have a look quickly at example 8.10. Example 8.10. You have to go and work through the examples again just to make sure that you understand before you go and do the basic problems. Determine the Q point for the JFET circuit in figure 822A. The transfer characteristic curve is given in 822B. So for ID, remember I have to plot the 2 points for the load line. Just to show you again, that's what it would look like for a P channel. Né? That's what it would look like for a P channel. Anyway, let's see how this one was found. So for ID is equal to 0, we've seen that VGS is also equal to 0. The next point I do is where ID is equal to IDSS, and I go and calculate the value of VGS. I write it in with the broken lines. I determine that point and I plot that point. Then I can draw the load line. Where it cuts, you tell me there. You write there Q. That's where the Q point is. And then again with broken lines from there, you tell me and you write in what are the parameters for the Q point. Okay. If I give you the transfer characteristic curve, this is about 6-7 marks, which I think is Pasella, because it's easy, ne? All right. All right, that was example 8.10. Then just to end off on the self-biasing, that sentence on page 387, just below that example, I underlined as well. For increased Q point stability, the value of RS in the self-bias circuit is increased and connected to a negative supply, voltage supply. This is sometimes called the dual supply bias. But let's end here, and then the next, we're running out of time. The next time we get together, we will discuss the voltage divider bias. Then I will point out again to you all the formulas, the graphical analysis and so forth, and important to know the difference between the two, and of course with which device you are working. Okay, it concludes the lesson for today.